So, thank you very much for coming again. I would like to start second lecture today. Okay. This is the issue, body kinematics and dynamics toward robotics. So I use same picture again. Brain has many function: cognition, language, learning, memory, and consciousness. More. Such a differentiation depending on the region of the brain on integration of the function module is really necessary to provide this function. The key point to understand this mechanism, okay, we have brain body. Brain body coordination is very important. More particularly, central nervous system is forms of the brain. The peripheral nervous system connects individual muscle and bones or some other organization. Then body and sensor connect peripheral nervous system and central nervous system. Then it computes and input and output. So motion and perception has a similar the problem. And dynamic motion, the problem with the degree of the freedom is also the issue, the constraint and the mechanism. The body moves to generate specific function, the motion, by adding some constraint functionally. As you experienced, the binding problem exists in the perception issue. Okay, GESTALT is recognized in your eye by using different mechanisms, the brain. So this kind of issue is we realize the brain mechanism as the actual experimental evidences, but not so easy to implement actual robot. In this lecture, I try to focus the behavior or generation of motion or control issue. This is a famous architecture, zero moment point method, or ZMP method in the robotic walking. There's some, okay, plate connecting leg is actually foot for the robot. There's some area. If center of the mass located inside of the this state space, it's no problem that the robot lifting the body very precisely. Or if inside of the portion, the connecting two legs attached to the ground, this theory tells if one leg is staying attaching the ground, and center of mass should be inside here, or if there's a multiple legs that attaching the ground, center of the mass should be located inside the this rectangle. This is kind of the control paradigm in the Coriolis, or the gravity and the reaction and the action with robot should be integrated together. Then finally, it exhibits the specific the movement of the center of the mass according to the foot position because of the ZMP motion. It quite nicely works, even if the Ashimo is working for this the architecture, but it's quite different actual movement, the motion, the behavior in the real animal and the human beings. This is the movement trajectory, the center of the mass aside the legs position. This is quite smooth, not like the robot. Mechanisms are different between robots and animals. Therefore, there's so many different motion generated very dynamically. Human motion are very dynamic. Start, dash, stopping, side step, and lifting up their oblique by 2. This is a periodic movement composed the body motion. 3 local function is called. Then there's some constraint of the bone, the muscle. Heel locker is generated some at the point is attaching in the ground, then the rotation happening. Another kind of the local motion, leg joint locker, is generate the centralized at this point, and 4-leg locker is the your tooth, the toe of the leg foot is attaching the ground, and 4-leg locker is happening. So therefore, this 3 local function, it behaves like a rocking chair. Okay, then your walking pattern nicely and naturally generated. I'm using same picture, the video coming from the NHA TV program. This is the general the exhibition of the snake motion generated by the peripheral nervous system. It's called central pattern generator, CPG. CPG is embedded in the animals, in the vertebrate animal, at the backbone. Has the nervous system inside. It generates some specific behavior. This is quite nicely works well, even with the snake, fish, and human being, like a rocking chair mechanism. Interestingly, even the snake or humans, we have a common principle to generate such as periodic motion. Even the cat. This is the detailed mechanism, how brain works to generate such a periodic pulse. The muscle movement, okay, this is very sad experiment with using cat. If you cutting off such a connection central nervous system to connect the peripheral nervous system, but some local circuit generate periodic pattern. So in that cases, it's a quite similar for the people have the accident, the neck, especially and happening in the drive accident. They have some function peripherally, even if it's not connected to the central nervous system. If treadmill is running, the cat walk clearly generated. Even there is no connection to the central nervous system, and if you can not consciously aware how you can behave, but the peripheral nervous system at the local circuit, the brain connects to generate this periodic pattern sequentially 1, 2, 1, 2, 1 to 3, 1 to 3, 1 to 3. It's a motion, the left leg and right leg, left leg and right leg is repeatedly moved naturally because this is embedded mechanism, natural property. This is called central pattern generator and the spinal cord. This is connecting usual cerebrum, sight, hearing, the vestibular sensation or proprioception is connected here. Interneurons, rhythmic generator and pattern generator and the motor neuron is connecting its local circuit in your brain at the backbone in a sense that actually called spinal cord. It's connecting the muscle too. Skeletal muscle, it generates such the repeated motion. That's why local chair movement happening. Then we can walk. But unfortunately, some of the case, the damage of the brain, there are some deficit to the function, the coordination, the motion. Therefore, some specific the disease we have. Proprioception is that exists in the muscle, even if the human muscle, but also the insect muscle. The next question, how we can generate this kind of rocking chair motion? What kind of mathematics that can explain this the mechanism of the phenomenon? This is a famous paper. Now this is a kind of the Bible or the roboticist. My senior, the Professor Gentaro Taga, it proposed a synchronization mechanism inside the robot. This is a kind of schematic illustration and the phase space, limited circle, and the closed loop equilibrium state is happening because of the leg is motion, the generating left, right, left, right, left, right, a kind of repeated rotation. It can be represented the state space in a form of the limited cycle, a limit cycle. There are two differential equations. One is the musculoskeletal system. Muscle, it repeatedly move. It can be described the differential equation and the nonlinear description. It connects its environment. So then the force reaction, then control is happening. It can be described Newton-Euler equation. Sensor feedback and the model command is also generated. Then how we can add such a constraint to generate some specific pattern. It is coming from CPG, neural rhythm generator. It also can be described nonlinear the differential equation with nonlinear term. This is the proposal of him. There's a hypothesis him. Then he tested it. In the computer simulation, the robot, he described body dynamics. And by solving Newton-Euler equation by computer simulation, and neural rhythm generator also given in the same simulator. Body kinematics clearly describe the physical way, the kinematics, the dynamics. And then neural rhythm generator like a metronome, but the metronome way. And then so many the rhythmic generator is connected together to control individual joint motion. He demonstrates it works well. In fact, it's a surprising thing that moment. It published 1995. It's worse. It's a what is a surprising thing? This is the formulation principal publication. Here's PhD thesis. Outstanding way. So the brain, nervous system, body, it can be coordinated in this consistent way. If you put perturbation, the noise, or adding force, but then this motion pattern clearly reconstructed in the sense of the rhythmic generator limit cycle, then such a consistent walking pattern regenerated after the disturbance. Even the slope, speed of the motion bit different, but it's clearly generated naturally. Environmental change is this system this very robust against the disturbance, the noise of the sloping road or environmental changes. This is the power of the differential equation and the nonlinear formulation. Walking pattern, the running is clearly generated by this system, same parameter, but generated different the phenomena from same system. If stationary input is increasing, so walking pattern generated rapidly, then the increase in the speed of the motion, then finally it jumped to the transit to the running pattern like this. This is naturally generated such in the sense of the bifurcation of the nonlinear the phenomena from same system. I would like to shortly introduce such a musculoskeletal system dynamic model of this. It's very outstanding work in that moment. He solved differential equation to describe Newton-Euler equation to represent robotic motion by hand. I was so surprising things that he did and the big contribution. He did this work in the PhD season. It is nice. And he also, inspired the Professor Matsuoka, Kyushu Institute the Technology, Kyotech here. He created the professor here all time, but he proposed such a nonlinear oscillator in this form, very simple form. It's generated CPG, and hip, knee, ankle is coordinated synchronously. That's why this behaves naturally. This rhythmic generator represented by the following differential equation very nicely and connect them together. This is a picture given by my PhD student, Kazuko Moda. He described it as this system. Okay, central nervous system and related musculoskeletal system by relation, the body and the brain, and the environment connect them together. Then there's some formulation. The phase space represent the gait, the different gait, different motion pattern in the state spaces. The mapping exists in the coordination, the Jacobian matrix, and the adjustment happening in the parameter tune in the working space. This is a kind of the formulation of the schematically what brain and robot behave. We thought what kind of the contribution is possible in the actual robot in the sense of the such a CPG inspired concept in the part of the brain inspired robotics. So many robotics try to think open linkage first. Okay, you may think about manipulator. Arm is extending, connecting them together. ZMP locomotion control is possible. But it requires a kind of the mechanism to minimize degree of the freedom. In the Professor Taga's case, CPG may work well, but in a sense, more traditional technique principle exists in from the old history. It's called closed linkage. So many machine or vehicle or mechanical system use this linkage. This linkage has a different system, but very simple because we do not focus too much about the control paradigm. This is funny guy. I respect him as an artist, of course.
I could show you this animal. Thank you. So the proportion of the tubes in the
Mechanical beasts will not get their energy from food, but from the wind. The wind will move feathers on their back, which will drive their feet. The beast walks sideways on the wet sand of the beach with its nose pointed into the wind.
That's only
As soon as it walks into either the rolling surf or the dry sand, it stops and walks in the opposite direction.
according to the such as,
This is the Animaris currens ventosa.
Thank you.
So this is the Theo Jansen and a kinematic artist. I respect him. I was so surprised to see the first time this mechanism because this is quite similar of the mechanism, the CPG, in the sense of the machine. There are some similar mechanism proposed, very old time Chebyshev mechanism, making it formed by the linkage, very working pattern generate in simply. Cram mechanism, 1994 is provided, kind of the mimic the mechanism to mimic the spider motion. Theo Jansen, 1990, he's providing smooth trajectory in this sense by linkage. I was so interested with Kazuko model, the S-kind model to represent our brain body issue. Close linkage are kind of the target mechanism body. Then we usually think about neural computation to control this motion, but it's kind of the modeling is possible to provide kind of functional motion by adding the constraint. This is a point of view how we can think about body kinematics, kinetics, and dynamics. Firstly, we focus the target mechanism besides of the controller. Therefore, we start to develop a method called match body dynamics. This is also traditional and develop the mechanism, the method to analyze multiple system. To deal with the match body systems, match body dynamics is proposed. Initially, is the Keynes motion equation that's very important. And then Keynes working in the NASA at launching the rocket to control the motion, the machine precisely, even in the space. Okay, Schuhelen and Everhard is proposed that such a combination relative coordinate system adding equation recursively. Newton-Euler equation is solved by the Gentaro Taga. I just demonstrated the picture. He solved by hand, but Schuhelen systematically introduced a very fine way to generate the description. Hang and Niklavich introduced differential algebraic equation. Now he's introduced global local coordination, the listing the systematical constraint equation. Then linear algebra comes back again, connecting differential equations. I really love the work that came. I did a respected person and a representative person at the Stanford University, and he's contributing so many projects in NASA space mission. This is very simple, but very interesting and inspiring. The paper that came is explaining cat walking, why you can put the cat, but the cat is rotating naturally, then reach the ground. Oh, why? He explained this mechanism, simple model. Okay, two drum is connecting some specific point, and rotating. According to the function of the gravity, this drum is rotated naturally, then attaching here. This can be explained theoretically very nicely. This is the power of the mathematics. Then I recommend you to learn the system. This is the point. There is tiny cat at the funny cat. So therefore, I would like to introduce you to learn the multi-body dynamics analysis. So many big effort done by Professor Gentaro Tanga, but we do not do the same thing anymore. You just simply understand the mathematics, then systematically solve, even by computer. Acceleration equation can be solved here in this way. This is the kind of matrix. Variation equation can be solved to treat the motion equation in the specific matrix form. Differential algebraic equation is treated by Jacobian, the generalized coordinate system way. Then this is the inverse kinematics. You may know the kinematics and the inverse kinematics. Normally, we can formulate the target position and the rotation and the angle, the leg and the hand. So then inverse kinematics said what kind of the joint motion is necessary to move some specific target motion. More seriously, what kind of torque is necessary for some specific action. This is the kind of estimation of the force and the torque and to generate some specific action. That's really necessary for any of robotics. So therefore, target mechanism, close linkage. Once you understand the multi-body dynamics, now I do not discuss over here the formulation now, but just I'm demonstrated how it works well. We are describing this Chebyshev mechanism, simply described this constraint equation. Then similarly, Cram mechanism can be described this way. This is not coming by hand. It's a systematic computational treatment. We usually use MATLAB, okay? The symbolic math. Then the Seo-Janssen mechanism can be described in this way. Bit more larger the matrix size, the vector size. Finally, we apply this the conversion of the generalized coordinate into the generalized coordinate, kinematic constraint, Jacobian acceleration equation, then compute the differential algebraic equation, then simulate how it works well. This is the locomotion analysis, the trajectory acceleration. Once you formulate this way, the computer calculates the motion and torque, the acceleration. And the Cram mechanism also exhibits some specific trajectory, the movement of the tooth toward the leg. And then Seo-Janssen mechanism provides such a smooth motion. The bottom picture is a represent the speed of the acceleration of motion, how it force or the acceleration generate. It's clearly described, speeding up, slow, or speeding up, falling down. And then the Seo-Janssen mechanism is naturally lifting up, then gradually touch the ground very smoothly. Then such as the walking at the speed and duty factor analysis possible by computation here. And comparison the speed duty factor also possible in this computation. Then power consumption can be analyzed in the computer simulation. Therefore, energy consumption can be estimated by this computer simulation based on the multi-body dynamics. Power consumption can be described this way. Then we try to normalize this comparison in different mechanisms. Average power, okay, TBGF may need the high power, but Taoyuan is need less power. That is true. The why Taoyuan mechanism works only by wind power. Energy consumption can be analyzed in this way in the duty factor. And then comparison the energy consumption is described in here. Then finally, specific resistance is it's kind of normalized power. It's proposed by the Gabrieli and Kalman, 1950. And then specific resistance, it works well for the normalized comparison with the other machine, how much they need the power or the energy. We analyzed such a comparison, the specific resistance against the working velocity. Similarly, Gentaro Tanga did. Chebyshev mechanism, okay. And similarly, exhibited power consumption was in the form of the specific resistance at the beginning. But if speed of the motion increase, Chebyshev takes more energy. Then clamp mechanism bit more, but Taoyuan mechanism, okay, keep less power, even if the high speed, okay. We analyze the comparison other type of robot. So many robots is already proposed in the United States or some other countries. So many type of robots that are provided. Oh, my robot is the best. No, my robot is the best. They do not compare the machine that they insist, okay, this is the best robot. But we are analyzing such a specific resistance against the working velocity. And then these mechanisms have some tendency have the specific resistance in the energy consumption and different types of points. We realized, okay, some passive worker have the very less energy. Taoyuan finally save their own energy, even if the comparison other mechanism. Okay, this black line is a kind of the energy consumption in the form of the specific resistance according to the working velocity. They're very high energies, energy consumption is takes, and depending on speed, power. Interestingly, those machines have some specific the best velocity to reduce the energy consumption naturally decrease according to the working velocity. It may be it comes back again. In the comparison the other mechanism, the Taoyuan have very less energy if working velocity is in the midpoint. But it takes large energy if fast the working velocity is high. You can simply imagine, okay, your energy can be saved in some comfortable the working speed. But if you request the working speed is high, running speed is high, your energy is consumed very much. And then you are very more comfortable riding the bicycle or the machine. Okay, this is the situation. Then this is the clearly visualized and analyzed in the mathematical way. This is the power of the multi-body dynamics. I will show you some other mechanism. helix and core. It's a very simple mechanism working well in the rough condition. But depending on cases, it's a small size robot. It's working well, but it's bigger. Okay, it's very tough for the moving the same way. So this is another robot. So another, this is the passive walker.
This familiar toy is a passive dynamic walker. With energy supplied by falling weight and the right start, it settles into a steady walking cycle sustained by an entirely passive interaction of gravity and inertia. This machine is also a passive dynamic walker. For that matter, I may be a passive dynamic walker. As you'll see, our gaits are quite similar. The camera was running the day when the analysis and my intuition were brought conclusively into line. Those few steps convinced us that we had the dynamics right. The reason the machine failed was a problem called knee bounce. So for later experiments, we went to a set of mechanical catches, and the next sequence shows our first trial with those. Oh, yes. I guess they work.
It works, even if there's no adding force or actuator. This is also funny motion. Creeping up. It's not always works well. Yes, this kind of the architecture that you may try to rebuild by yourself, physically or virtually now. I just simply recommend to learn the mathematics in the sense of the multi-body dynamics. I would like to summarize today's topic. Okay, this robot is possible, a kind of the sense of the embodiment. You may try to reconstruct some of the biological motion in a simple way. Yes, this is the right answer in a sense. If you want to focus on simple the dynamics of the motion. If we really want to, the whole mechanism, brain and body, and how robot, the brain, the human generate the creative motion or the action, you need to think about more about central nervous system. The musculoskeletal system itself is connecting the peripheral nervous system to generate some specific motion and action pattern, but this is limited in the sense of the planned motion. Therefore, a very important point is that mapping of the environmental space, niche, and mapping on the system and Jacobian matrix, like I showed, multi-body dynamics. We can describe what kind of the behavior happening at the solution, and phase space can be can explain the mechanism, what kind of pattern it can be generate a solution in the adding constraint. Our paper is already published in 2017 and Kazu Komura and Hiro Wagatsuma, and you can find multi-body dynamics. It's a Q1 journal, and you can find this system more in detail. Thank you very much for the kind attention today. So is there any question today? Now? It's okay? Okay. Okay, please, if you enjoyed my lecture today, please show the thumb up or the reaction. Thank you so much. Thank you so much. Okay, I really appreciate again the comment of the KW system. I try to reply. Unfortunately, still we have the 20 number of the student here, but I try to join this again. Okay. Okay, thank you very much again for taking time, but I really appreciate your participation. And then I really love to the audience, the backside, and the connecting YouTube too. Okay, even if the online, on time, or recording video. I really hope that you have some time visiting Japan and our more cross discussion or some collaborative mission to make new type of robot together or artificial intelligence the session. Okay, thank you very much. If you have the comment, you can put some comment in the chat or now. Okay, that's it. Okay. Okay, thank you very much again. I'll see you tomorrow again. Thank you so much. Okay.
Thank you, sir, for your lecture.
Thank you very much.